Look around you right now. The water in your glass, maybe the air you're breathing, definitely the salt on your food. None of it, well, almost none of it, is just pure elements floating around.
Hmm.
It's all these incredibly complex, interconnected substances. What are the fundamental principles that govern how these things even come into being, how they hold together?
Right. And how do we even start to describe them?
Exactly. How do we make sense of it all?
Well, it really boils down to how elements, the universe's basic building blocks decide to combine. And there are rules, very specific rules, governing those combinations.
Okay.
So today we're taking a deep dive into chemical compounds. Specifically, we're looking at the foundational ideas of ionic and covalent bonding.
Right. The two main ways atoms get together.
Precisely. Our aim here is to give you a shortcut, sort of, to truly understanding the language of chemical formulas, what those little letters and numbers really mean.
That's our mission then. We want to uncover how these compounds actually form, how we name frankly, bewildering variety of them that exists.
Millions of them.
Millions. And crucially, how we can actually measure and quantify these tiny, tiny things. So hopefully, you'll leave with a clearer grasp of the architectural rules governing the world around us.
Let's do it.
So let's start at the beginning. A compound. What is it fundamentally? It's a substance made when two or more different elements chemically combine.
And the key phrase there is chemically combine in a very specific fixed ratio.
Right. It's not like just mixing salt and pepper. You can't separate a compound easily by physical means. You can't just filter the hydrogen out of water, for instance.
No, it's fundamentally H2O. And the real players, the architects behind these combinations, are the valence electrons.
Ah, yes, the valence electrons, not just any electrons.
No, these are the ones in the outermost energy shell of an atom. They're the ones actually involved in chemical interactions, the ones doing the negotiating, if you will.
That's a good way to put it. And to help us visualize this negotiation, chemists use something called Lewis dot symbols.
Very useful shorthand.
Yeah, you just imagine the elements symbol, like Na for sodium, and you surround it with dots. Each dot represents one valence electron.
And for the main group elements, the ones in the tall columns on the periodic table, it's beautifully simple. The number of dots is just the group number.
Instantly tells you something about its potential behavior.
Exactly. And it's amazing how predictive these simple dots are. For metals, like sodium, the number of dots usually shows how many electrons it's likely to lose to become stable, forming a positive ion, a cation.
Okay.
But for nonmetals, especially, say, in the second row, the number of unpaired dots often tells you how many bonds that atom is likely to form. It gives you a clue about its bonding capacity.
So it's predictive power in a simple visual. And you can even draw these for ions, right?
Absolutely. If an atom gains electrons, becoming an anion, like fluoride, F-, you add the extra dots to show it achieved a full shell. Then you put square brackets around it and the negative charge outside.
Visually showing that stable configuration.
Right. But for a cation, like potassium, K+, it loses its single valence electron. So the Lewis symbol for the ion actually has no dots. It just shows the K+ symbol representing the stable core underneath. No brackets needed, usually, because there are no valence electrons left to show.
It's like a snapshot of the atom after it reached that stable noble gas configuration it was aiming for.
Precisely.
Okay, so we understand the players, the atoms, and their valence electrons. You have the real action. How do they actually connect? This brings us to the two main types of chemical bonds. Let's start with maybe the more dramatic one, ionic bonding.
Good starting point.
Yeah.
Ionic bonding is fundamentally about electron transfer. One atom essentially gives electrons away, another accepts them.
A give and take.
A complete give and take. It typically happens between elements with very different tendencies. You have elements that lose electrons easily, typically metals, low ionization energy forming positive cation.
Like our sodium example.
Exactly. And elements that readily accept electrons, typically nonmetals, high electron affinity forming negative anions, like chlorine. So imagine that sodium atom donating its one valence electron to a chlorine atom. You end up with Na+ and Cl, positively charged sodium, negatively charged chloride.
Opposites attract.
Very strongly. That electrostatic attraction between the positive Na+ and negative Cl ions is the ionic bond. It holds them together in an electrically neutral compound, sodium chloride, forming this vast, highly ordered three-dimensional network.
The crystal lattice.
The crystal lattice, yes. Extremely stable.
And we can actually put a number on that stability, can't we? lattice energy.
We can. Lattice energy is technically the energy required to take 1 mole of that solid ionic compound and completely separate it into its individual ions in the gas phase.
That's a measure of how strongly they're stuck together.
Exactly. The higher the lattice energy, the stronger the ionic bonding in that crystal.
And what determines how high that energy is?
Two crucial factors. First, the magnitude of the charges on the ions. Higher charges mean stronger attraction. Second, the distance between the ion centers. Smaller ions can get closer, leading to stronger attraction.
Okay, let's make that concrete.
Yeah.
You mentioned comparing similar compounds.
Right. Think about lithium iodide, sodium iodide, potassium iodide, same anion. But the cations, Li plus I, Na plus I, K plus I, get bigger as you go down the group in the periodic table.
So the distance increases.
The distance increases, and so the lattice energy decreases. They're held together less tightly. But the charge effect, that's often much more dramatic.
Oh, so?
Compare lithium fluoride, Li plus F, with magnesium oxide, Mg2 plus O2, and maybe even scandium nitride, Sc3 plus N3. The ion sizes aren't wildly different, but look at the charges. +1 - 1, then +2 - 2, then +3 - 3.
Oh, yeah.
As those charges go up, the lattice energy just skyrockets. It increases massively. And this isn't just, an abstract number. It explains real-world properties.
Like what?
Well, why magnesium oxide has such a high melting point used in furnace linings, or why compounds with highly charged ions might be very hard, very brittle ceramics. It connects directly to material properties.
Okay, so that's the drama of electron transfer in ionic bonds. What happens when atoms are maybe less inclined to just give up or grab electrons? When a full transfer isn't favorable?
That's where the other side of the coin comes in. Covalent bonding. Here, atoms achieve stability not by transferring electrons, but by sharing them.
Sharing is caring, even for atoms.
Sort of. Gilbert Lewis, who gave us the dots, also laid the groundwork here. Think of two hydrogen atoms. Each has one electron. Instead of one giving to the other, they each share their electron, forming a pair between them, H:H.
Right.
That shared electron pair is the covalent bond. It holds the two hydrogen atoms together. And when atoms are joined by covalent bonds, we usually call the resulting neutral unit a molecule.
Okay, so a molecule is this distinct package deal held together by shared electrons.
Exactly. And a molecule can be an element like H2 hydrogen gas or O3 ozone, which is polyatomic, or it can be a compound like water, H2O, or carbon dioxide, CO2. The key is it's a neutral combination of atoms in a specific arrangement, often with very specific shapes, which we'll get into another time.
And these combinations, like in ionic compounds, aren't just random mixtures. There are rules. You mentioned the law of definite proportions.
Yes, a cornerstone principle. It basically says that any pure sample of a given compound, no matter where it comes from or how it was made, always contains the same elements combined in the same proportions by mass.
So CO2 is always CO2. By mass, it's always about 2.66 grams of oxygen for every 1 gram of carbon. Always.
Always. Whether it's from burning wood or from your breath, it's like a fixed recipe. And building on that, there's the law of multiple proportions.
Right, because sometimes the same elements can combine in different ratios to make different compounds.
Precisely. Think carbon and oxygen again. They make CO2, carbon dioxide, but they also make CO, carbon monoxide, very different substances.
Definitely want CO2 in your soda, not CO.
Absolutely not. Now look at the mass ratios. In CO2, it's 2.66 grams oxygen per gram carbon. In CO, it's 1.33 grams oxygen per gram carbon.
Okay.
Now compare those two ratios. Divide the ratio in CO2, 2.66, by the ratio in CO, 1.33. What do you get?
2.66 divided by 1.33. That's exactly 2.
A small whole number, 2 to 1. That's the law of multiple proportions. When two elements form more than one compound, the ratios of the masses of the second element that combine with a fixed mass of the first element will always be ratios of small whole numbers.
Wow. Okay, that sounds a bit dense, but the example makes sense. It's showing that atoms combine in these fixed, discrete, whole number ways.
Exactly. This was huge for John Dalton and the development of atomic theory. It was powerful evidence that matter wasn't infinitely divisible, but made of discrete atoms combining in specific ways. It laid the groundwork for writing chemical formulas like CO and CO2.
So for you listening, the takeaway is this underlying consistency. Whether atoms transfer or share electrons, they do so in predictable, fixed ratios, leading to distinct compounds with reliable properties.
It's the basis of chemical predictability.
Okay, so we have millions of these compounds. Naming them all must be a nightmare if you don't have a system.
It would be impossible, which is why chemists develop systematic nomenclature, basically, a universal language for naming substances. It ensures clarity, avoids ambiguity.
So where do we start with this language?
The simplest are monatomic ions, ions made from single atoms. For catentions, the positive ions, it's usually just the element name plus the word ion. So K plus is the potassium ion, Na plus is the sodium ion.
Easy enough. What about anions, the negative ones?
For monatomic anions, you take the element's root name and change the ending to iide. So Cl becomes chloride, O2 becomes oxide, N3 becomes nitride.
Okay, so potassium plus chloride gives potassium chloride. Oxide plus sodium gives sodium oxide. Makes sense.
Right. But there's a complication. Some metals, especially the transition metals in the middle of the periodic table, can form charges with different positive charges. Iron is a classic example.
Ah, yeah. Iron can be +2 or +3, right? F2 plus and F3 plus red.
Exactly. So just saying iron ion isn't specific enough. This is where the stock system comes in. We use Roman numerals in parentheses right after the metal's name to indicate the charge.
So F2 plus is iron 2.
Iron 2 ion, yes.
Okay.
And the 3 plus is iron 3 ion. So you'd have iron 2 chloride or iron 3 oxide. The Roman numeral removes the ambiguity.
Very clever. Okay, so we have names for the ions. How do we write the formula for the compound they make, like your aluminum oxide example earlier?
The golden rule for ionic compounds is electrical neutrality. The total positive charge must exactly balance the total negative charge.
Right.
Aluminum is typically Al3 plus Hon. Oxygen is typically O2. To make them balance, you need the smallest number of each ion so the charges cancel out. The least common multiple of 3 and 2 is 6.
Okay.
So you need 2 Al3 plus ions to get a total charge of +6, 2 times +3. And you need 3 O2 ions to get a total charge of -6, 3 times -2.
+6 and -6 cancel out.
Neutral. So the formula is Al2O3, 2 aluminums, 3 oxygens. This crisscross method, where the magnitude of one ion's charge becomes the subscript of the other, often works, but understanding why the need for neutrality is key. It's a common sticking point sometimes.
Got it. So the formula comes from balancing charge. Now, naming the compound itself, Al2O3.
For simple binary ionic compounds like this, you just name the compation first, using the Roman numeral if needed, then name the anion. So Al2O3 is aluminum oxide. FeL2 would be iron 2 chloride. FeL3 is iron 3 chloride.
Notice you didn't say anything like dialuminum trioxide.
Correct. For ionic compounds, we generally don't use prefixes like di, tri, tetra. The charges of the ions themselves determine the ratio. Once you say aluminum and oxide, chemists know aluminum is +3 and oxide is -2, so the formula must be Al2O3 to be neutral. The ratio is implied.
Okay, that's an important distinction. No prefixes for simple ionic compounds. But what about those more complex ions you mentioned, polyatomic ions?
Ah, yes. Polyatomic ions are fascinating. They are groups of atoms, like sulfate SO4 or ammonium NH4, that are joined together by covalent bonds internally.
So sharing electrons within the group.
Exactly, but the entire group carries an overall net charge. Sulfate SO4 has a 2 charge, ammonium NH4 has a 1+ charge, and they act as a single unit when forming ionic compounds.
Like little molecular ions.
Pretty much. And when you need more than one of these polyatomic units in a formula, you have to use parentheses around the ion before adding the subscript.
Give me an example.
Okay, calcium phosphate. Calcium is K2 plus I. Phosphate is a polyatomic ion, PO4-3. To balance the charges, you need 3 CH2 plus, total +6, and 2 PO4-3, total land at 6.
So the formula would be She3, then the phosphate part.
C3, then parentheses PO4, then the subscript 2 outside the parentheses, C3, PO4-2. The parentheses make it clear the 2 NATs applies to the entire phosphate group, 2 phosphorus atoms and 8 oxygen atoms in total from the phosphates.
Right, the parentheses group the whole polyatomic unit. Makes sense. And within these polyatomic ions, especially the ones with oxygen-oxoanions, there's even more naming system, right? Prefixes and suffixes.
Yes, there's a beautiful system for families of oxoanions. Take the chlorine oxoanions as an example. Chlorate is ClO3. That's sort of the baseline.
Okay, chlorate, ClO3.
If you have one more oxygen, it becomes perchlorate, ClO4.
Pu means more. Got it.
If you have one less oxygen than chlorate, the ending changes from ate to ite. So ClO2 is chlorate.
8 becomes ite for one less oxygen.
Right. And if you have 2 less oxygens than chlorate, you keep the ite ending but add the prefix hypo, meaning under or less. So chlora is hypochlorite.
Wow. Per 8, 8 ite, hypoite. That covers a range of oxygen content systematically.
It does. Perchlorate, chlorate, chlorite, hypochlorite. And this pattern applies to other families too, like bromate or iodate. It encodes structural information right into the name
That's really elegant. And does this connect to naming acids, too?
directly. Acids can often be thought of as combining H plus ions with anions. If the anion ends in ate, the corresponding acid ends in eke acid. So from chlorate, ClO3, you get chloric acid, HClO3.
8 goes to ic acid.
If the anion ends in ate, the corresponding acid ends in hapechlorous acid. So from chlorite, ClO2, you get chlorous acid, HClO2.
8 goes to aqueous acid. What about simple anions like chloride, Cl?
If the anion ends in ikide, the acid name starts with hydro, keeps the anion root, and ends in achaic acid. So from chloride, Cl, you get hydrochloric acid, HCl.
Hydrochloric acid. Okay, that raises a question, though. You just called HCl hydrochloric acid, but sometimes it's called hydrogen chloride.
Ah, excellent point. Context matters. HCl as a pure gas is typically called hydrogen chloride. But when that gas dissolves in water, it forms an acidic solution, and that solution is called hydrochloric acid.
So the name can change depending on its state or environment.
Yes, particularly for acids. The aqueous solution often gets the acid name.
Fascinating. Okay, one more category. Hydrates. What are those?
Hydrates are ionic compounds that have a specific number of water molecules trapped within their solid crystal structure. They're not just wet, the water is part of the formula unit.
Like chemically bound water.
Loosely bound, but in a fixed ratio. A common example is copper sulfate pentahydrate. Its formula is written CuSO4.5H2O. The dot indicates the 5 water molecules associated with each CuSO4 unit.
And that penta prefix means 5 waters.
Exactly. D, tri, tetra, penta, hexa indicate the number of water molecules. And these water molecules can often be driven off by heating. When copper 2, sulfate pentahydrate, which is blue, loses its water, it becomes anhydrous copper 2 sulfate, KuSO4, which is a white powder.
So the water can really affect the properties, even the color.
Dramatically. And finally, we can't forget common names.
Right, like baking soda or vinegar.
Exactly. Or things like milk of magnesia, which is magnesium hydroxide, or laughing gas, which is dinitrogen monoxide. These names often stick around due to history or common usage, even though they have systematic names too.
So a rich system, but also some history baked in. Okay, we know how to name them. How do we actually measure quantities of these incredibly tiny things?
That's where we bridge the microscopic and macroscopic. We start with atomic masses from the periodic table. For a molecule, like water, H2O, we find the molecular mass by simply adding up the atomic masses of all the atoms in the formula.
So 2 hydrogens and 1 oxygen. Add up their atomic masses.
Yep. For ionic compounds, like NaCl, we do the same thing, add up the atomic masses of Nal and Cl. But technically we call it the formula mass instead of molecular mass, because ionic compounds don't form discrete molecules in the solid state.
But the calculation is the same.
The calculation is identical. Add up the masses of the atoms shown in the formula unit. And these masses are typically expressed in atomic mass units, a mu.
Okay, mu. And you mentioned earlier these are average atomic masses.
Crucial point. Most elements exist naturally as a mixture of isotopes atoms with the same number of protons, but different numbers of neutrons, so different masses. The atomic mass on the periodic table is a weighted average based on the natural abundance of these isotopes.
So it reflects the reality of the elements as we find them.
Precisely.
Okay, once we have the molecular or formula mass, what can we do with it? Percent composition.
Yes. Percent composition by mass tells you what percentage of the compound's total mass comes from each element within it.
How do you calculate that?
You take the total mass of a specific element in the formula, like the mass of 2 hydrogens in H2O, divide it by the total molecular mass of the compound, H2O, and multiply by 100%.
So for H2O2, hydrogen peroxide, you'd find the mass of the 2 H's, divide by the total mass of H2O2 times 100, then do the same for the 2 O's.
Exactly. For H2O2, it works out to about 5.9% hydrogen and about 94.1% oxygen by mass. It tells you the elemental breakdown by weight.
And why is that useful?
Well, imagine you're synthesizing a compound or analyzing a drug like lithium carbonate, which is used as a mood stabilizer. Calculating the theoretical percent composition and comparing it to what you measure experimentally is a fundamental way to check the purity of your sample.
Ah, so it's quality control. If your measured percentages don't match the theoretical ones for pure Li2CO3, something's wrong.
Something is definitely off. It's a routine check in many labs.
Okay, this is all still working with relative masses. How do we connect these tiny mu values to the grams we can actually weigh out in a lab?
This is the magic bridge, the concept of the mole.
The mole, chemistry's favorite number.
It really is. The mole is just a specific number of things, like a dozen means 12. A mole means Avogadro's number of things.
Which is huge.
Immense. 6.022 times 10 to the 23rd power. 6.022 by 1023 particles, whether atoms, molecules, ions, whatever.
An almost unimaginable number. Why that specific number?
It's defined as the number of atoms in exactly 12 grams of the carbon-12 isotope. This definition creates a beautiful link. The mass of 1 mole of any substance in grams is numerically equal to its atomic, molecular, or formula mass in a mu.
Hold on, say that again.
The mass of a single carbon-12 atom is 12 a mu. The mass of 1 mole, 6.022 by 1023, of carbon-12 atoms is exactly 12 grams. The number is the same, just the unit changes from mu to gram small when you scale up to a mole. This quantity, the mass of 1 mole, is called the molar mass.
Okay, so the molar mass in Grossi has the same value as the formula mass in AMU. That's the bridge.
That is the bridge. It allows us to count atoms or molecules by weighing them. If you weigh out 12.01 grams of carbon using the average atomic mass now, you know you have 1 mole, or 6.022 by 1023 carbon atoms.
But you have to be careful about what substance you mean, right? Like with oxygen.
Absolutely critical. Oxygen gas normally exists as O2 molecules. The molecular mass of O2 is about 32.000 AMU. So the molar mass of O2 gas is 32.00 grams per mole. But if you were talking about individual oxygen atoms, the atomic mass is 16.000 AMU, and the molar mass of atomic oxygen is 16.00 grams per mole.
But you need to be precise about whether you mean atoms or molecules.
Always. Context is everything with molar mass.
Okay, so now we have moles, molar mass, Perle mole, and Avogadro's number, particles mole.
It can convert between this.
Yes, this is the heart of quantitative chemistry, or stoichiometry. You can convert grams to moles using the molar mass. You can convert moles to the number of particles, atoms, molecules, using Avogadro's number.
Yeah.
And you can go back and forth.
So if I have, say, 10 grams of CO2, I can find its molar mass, figure out how many moles of CO2 that is.
Yep. Grams divided by molar mass gives moles.
And then multiply moles by Avogadro's number to find out exactly how many CO2 molecules are in that 10 grams. Exactly right. Or you could start with a number of molecules and work back to mass. These conversions are fundamental tools for any chemist.
The backbone of quantitative chemistry, you said. Okay, one last piece. Can we work backwards? If we analyze an unknown compound and find its percent composition, can we figure out its formula?
Yes, absolutely. If you experimentally determine the percent composition by mass of an unknown compound, you can calculate its empirical formula.
Empirical formula, what's that?
The empirical formula is the simplest whole number ratio of elements in the compound. It might not be the actual molecular formula, but it's the simplest ratio.
How do you get that from percentages?
You essentially assume you have a 100-gram sample, so the percentages become grams. Convert the grams of each element to moles using their atomic masses. Then divide all the mole amounts by the smallest mole amount you calculated. This should give you ratios that are close to whole numbers, representing the subscripts in the empirical formula.
Okay, so percent to mass, mass to moles, divide by smallest moles to get the simplest ratio.
That's the process. Now, this gives the empirical formula. For example, you might find the empirical formula is CH2O, but the actual molecule could be CH2O, formaldehyde, or C2H4O2, acetic acid, or C6H12O6, glucose. They all have the same simplest ratio.
So how do you find the true molecular formula?
You need one more piece of information. The approximate molar mass of the compound, usually determined by a separate experiment.
Okay.
You calculate the mass of the empirical formula unit, the empirical formula mass, then you divide the experimentally determined molar mass by this empirical formula mass. The result should be a small whole number.
Like 1, 2, 3.
Exactly. That whole number tells you how many empirical formula units are in the actual molecule. You multiply the subscripts in the empirical formula by that whole number to get the molecular formula.
Let's try an example. You mentioned nitrogen and oxygen earlier. Say a compound is 30.45% nitrogen, 69.5% oxygen, and its molar mass is about 92 gmol.
Okay, convert percentages to grams, 30.45 grams and 69.55 grams. Convert grams to moles, divide by atomic masses. 2.17 mol N, 4.35 mol O. Divide by the smaller number, 2.17, gives 1 mol N and about 2 mol. So the empirical formula is NO2.
NO2. Got it. Now the molar mass part.
Tabulate the empirical formula mass for NO2, 14.01 plus 16.000 equals 46.01 gmol. Divide the experimental molar mass, 92 gmol, by the empirical mass, 46.01 gmol. 92 46.01 is almost exactly 2.
Yeah.
So the molecular formula is twice the empirical formula. Multiply the subscripts in NO2 by 2.
And 1 by 2 by 2O2.
Then 2O4, dinitrogen tetroxide. That's the actual molecular formula. So you see how experimental data, percent composition, and molar mass leads directly to figuring out the true formula of a substance.
That's incredibly powerful, from basic measurements to the exact molecular makeup.
It really is. It's how we identify new compounds and verify known ones.
Wow. Okay, so from the tiniest interactions of valence electrons, through the rules of ionic and covalent bonding, the systematic way we name millions of compounds, and finally, how we count and quantify them using the mole. We've really covered the fundamentals of chemical compounds today.
We've laid down some core principles. Understanding how atoms bond, how we name things consistently, and how we use the mole to connect the atomic scale to the lab bench scale. These are essential tools.
Absolutely. You really get a sense of the underlying order and predictability in chemistry. And these tools aren't just, for passing exams.
Not at all. This knowledge is the bedrock for everything from designing new materials with specific properties, stronger plastics, better catalysts, more efficient solar cells, to understanding the incredibly complex chemistry happening in our own bodies.
Right. Developing medicines, understanding how nutrients work.
Yeah.
It all comes back to these compound interactions.
It truly underpins so much of modern science and technology.
So, as a final thought for you listening, consider the sheer, almost infinite variety of compounds that can be built from just the 92 or so naturally occurring elements. Knowing these fundamental rules of bonding and composition allows chemists not just to understand what exists, but to design and create entirely new substances. What kinds of new materials or molecules may be addressing current global challenges could be possible if we really master and apply these core principles. Something to think about.